So with each of these materials, we want to look not only at how the material enabled builders to solve a problem or to achieve some sort of effectiveness or efficiency, we also want to look at what happens, remember, as Vitruvius says, once necessity is satisfied, how do we then turn the material into something expressive, right? Turn it into a built language. And we see examples of this in Roman brick construction in the way that they actually put the walls together and the resulting visuals that you see based on how the bricks are manufactured and actually laid. So we'll go kind of from the most utilitarian to sort of the most formal. And the Romans used not only the materials of the wall, but also the way the materials were shaped and laid out to indicate how important a building was. So to begin with, they made walls often that were just what we today would call rammed earth, basically using cementitious material and dirt to make a sort of slurry of mud and mortar that would eventually sort of congeal into something more solid, right? Something that today we would think of as pretty weak concrete. And that we see examples of this often in sort of utilitarian works, but also in the bases of temples. So this is the Temple of Venus in the Roman Forum. We'll talk about the building in the back there a little bit later. But you can see that it has survived for a couple thousand years, and it's basically just rammed earth. In other words, mortar and mud that are piled into formwork that's made out of boards, as you see on the left. You can see in the photograph the imprint of the wooden posts that were used to hold the boards in place. And then after the boards are stripped, we don't know, there may have been a protective wall around this or not, but you can see that there is kind of aggregate. There's rubble, there's rocks and bricks and things that have just been thrown in to the mix. It's more or less at random. So there's nothing particularly celebratory about this. It's a utilitarian structure. These might have been dressed up with something on the outside or left plain in the case of sort of everyday public works. In building walls, Romans often combined brick exteriors with a core of opus cementitium, in other words, that rammed earth that we just looked at. And the brick often worked as the formwork itself. So you get the sense that they were either pouring the rammed earth and building the brick wall at the same time, the brick as a container for the rammed earth, or possibly in some cases that they were building most of the wall and then filling the void with rammed earth afterwards. More likely that things went up kind of in tandem, right? So that the brick and the core were going up at roughly the same time. The simplest way to do this is a technique called opus incertum, where random rocks and bricks are simply laid on the exterior. It's essentially just one face of rubble that's used and that requires probably a bit of formwork on the outside to hold things in place. And this has the appearance of a stone wall, so this is something that would be appropriate to an exterior wall, but maybe not a formal building. They used tetrahedral bricks that had a kind of point to them that would engage with the rubble on the interior core of the wall in a type called opus reticulatum. So this characteristic diamond pattern, what you're looking at in the surface of the wall is the square base of a tetrahedral brick. And then the point of the brick, as you can see from the drawing, is engaged with the rubble and cement core of the wall on the inside. So it's a way of creating a bonding between the sort of skin and the structural core on the inside. A little bit more formal, something that we see a lot in like warehouse construction or what we think of as sort of commercial buildings in a place like Ostia. And then for something more formal, more finished, they used a form called opus testaceum, which is the flat brick that we saw in the brick-making slides, low, flat, long bricks that are mortared together and that contain the core inside. If you look at the drawing, you can see this is where those flat sandwich-shaped triangular bricks are used. And again, just like in the tetrahedral bricks, that is a way of making sure that the skin, the brick skin, and the cement core are bonded together. And you can see in this type of wall, there very often are very large bricks or stones that go all the way through the wall that tie the two exterior walls together. And today we would think of that as being a way to prevent the fluid pressure of that cement core from pushing out against the wall or from making it sort of bow. And we see examples of this type of wall all over Rome and all over the former empire. This engraving by Piranesi maybe gives you a slightly better idea of how it worked. And then on the right, this is the actual wall that we think maybe Piranesi was looking at when he did the bit in the upper part of the drawing. This is from the baths of Caracalla, one of the great Roman bath complexes. And you can see the interior core is, some of it is laid brick, some of it is just brick that's kind of thrown in. But most of it down at the base, you can see that it's also rubble, so just stones and whatever was lying around to take up space. And then on the exterior, a very well laid skin of brick so that you get the structural performance of a very deep wall, but you're spending essentially the money on really good brick only on the outside. And this, again, was a type of wall that was deemed formal enough for something like a monumental public works complex, like a bath or a palace. Romans were very good at mixing and matching, so there's a type called opus mixtum, where in this case brick and tufa are used. This is one of the markers in the Circus of Maxentius, a chariot racing course that was just out of the city. And this is essentially just decorative. This is a way of turning the kind of mechanics of the brick wall into something a little more expressive, a little more architectural, right? I think of this as racing stripes on the marker that the chariots would race around. And for the most formal construction, so here an imperial tomb on the Via Appia, which is essentially the same construction, rubble and cement in the center, and then a skin, but a skin now instead of brick. Here the imperial family was able to spend the money on travertine, and that travertine is engaged at some points with the rubble, as you see in the drawing on the lower right. So some of those stones extend back into the wall to tie the skin to the rubble. Others of them are essentially just sort of plastered on, and you can see where a few of the travertine tiles essentially have been lost. So there's not only a kind of methodology to using the sizes of brick that are easy to make, easy to transport, easy to lay, but there's a way then also of turning that around and making an expressive language out of the bricklaying techniques that the builders were using. One thing that brick allows you to do is it allows you to get beyond the limits of trabeation. When we were talking about stone construction in Egypt and we looked at the Karnak Hall, we noted that the Egyptians were limited by the tensile strength of the limestone that they were using, that the limestone beams that they were using to bridge the hypostyle hall couldn't be long enough to get any real sort of sense of space, right? The columns have to be spaced very closely together. And one of the great realizations of the Roman era was that there were other ways to span a distance between supports. And brick and stone, but more, as we'll see, brick, lends itself very nicely to creating an arch or a lintel, something that allows you to go much further distances between points. Bill Addis, in his book Building, makes very clear that he thinks this is one of the great kind of leaps in human construction, that the arch and its extrusion, the barrel vault, which we'll talk about here in a second, allow you to make long spans out of small elements. In other words, you don't need to go find a giant tree trunk or a giant piece of stone to bridge a span. With these techniques, as we'll see, you use a technique called centering that allows you to build an arch or lintel out of small pieces, out of bricks that can be brought to work by hand. because arches and lintels both work in compression, and because stone and brick are good in compression, there's a natural fit between the structural type and the constructive technique. And you can bring all of these things to the job site by hand, right? You don't need oxen, you don't need horses to do it. The arch is a fairly complicated structural system if you're an ancient builder. And essentially what it does is you can think of it in a couple different ways. You can think of it as a beam that is shaped to sort of move out of the way of the tensile area, right? The tension always occurs in the bottom of a simply supported beam. So you can think of the arch as sort of being shaped so that it's only taking the compression loads of a typical beam. Or you can think of it element by element, and you can imagine each stone, or each voussoir as they're called, making sure that the stone above it is in equilibrium. In other words, taking the weight, the load of that stone, and transmitting it through itself to the next stone in the arch. Now, when this happens, what you're essentially doing is you're taking a gravity load and you're turning it into both an upward resistance, but also a horizontal one at the base. If you think about it, if you push down on an arch, what's going to happen is it's going to try to push its buttresses or its buttressing walls out, right? That's the way it's going to want to fail. The Romans realized this. They were very good at sizing their supporting walls to be adequate to both the vertical load, but also to the horizontal thrust that's implied by an arch. And they were sophisticated enough to develop what's called the flat arch, which you see in the upper right, where even though it looks like it's a straight rectangular beam, the shapes of the voussoirs essentially introduce an invisible arch, right? An arch that is perpendicular to the line between each voussoir. And what's happening there is that instead of geometrically getting out of the tensile region, what's happening there is it's just taking advantage of the equilibrium sort of definition of an arch. And each stone is reacting in a way that ensures the stone above it is supported, right, in both vertical and horizontal directions. Still a horizontal thrust that needs to be taken care of at the sides, but an effective way to span larger and larger distances. Now, what the Romans did not maybe realize, but which we know today through analysis, is that this is also a fairly safe way to build, that as you see in the central drawings, those buttresses will move, right? Every load involves some sort of movement, some sort of acceleration, and any arch will have its buttressing walls give a little bit when load is applied on it. And as you can see, even in a flat arch, that can be fairly significant. But so long as the arch maintains enough of its geometry to keep, as you see here, no more than 4 hinges, right? In other words, 4 places where one end or another of the voussoirs are in contact, the system will remain stable. You get into problems, as you see in diagram B, if the buttresses move so much that the stones of the arch begin to slide past one another, and that will lead to a failure in your arch or your vault. But there's a surprising amount of flexibility in how much those buttresses can move and still maintain the arch's structural integrity. And the same, incidentally, goes for lintels. When we were looking at Greek architecture, we looked at lintels, some of which we talked about having the possibility of cracking. And as you see in B and in C, it's very possible for what looks like a regular lintel to actually form a flat arch. And we see occasional examples of Greek stone engineering where the lintels are shaped as if they were a sort of rudimentary flat arch, as you see in diagram C. The most immediately obvious Roman arches are in the aqueducts, where they were building channels that occasionally had to be very high up in the air. These are bringing water down from mountain springs into the cities, and so they have to maintain a very precise slope. And that means they occasionally have to cross stream valleys or go through mountains. And so there's a whole civil engineering profession that involves tunneling and that involves the construction of these very tall aqueducts. And you can see from this example in Segovia that the arches are made out of stone, in this case, not brick. But it's a good way to see exactly how they work. One arched thrust is going to cancel out the other, essentially. In other words, the two arches are trying to flatten out in opposite directions, and they're resisting one another in that way. To make sure that any localized imbalance gets taken care of, between the two arches, there's a very, very heavy pile of stone shaped in a sort of upside-down triangle, and that actually has the effect of pushing or changing the trajectory of the arch's thrust toward the vertical, so lessening the amount of resultant thrust in one direction or another, making the other arch's job easier, basically, in resisting that thrust. And you can see that the arches sit on what looks like a sort of rudimentary column capital. And in fact, we think that is where the scaffolding for the arches probably sat. And I'll talk about that in a little bit, why the semicircular shape is one that we see again and again in Roman construction, and why in this case those little ledges are actually super important. So that's a simple semicircular arch in stone. And the advantage of brick is that you can fine-tune the shape of the arch to whatever the situation you have to hand actually is. So here are three examples of Roman lintels, spans over window or door openings, and you can see that there are a variety of ways in which the masons have handled that, transferring the load of the wall above to the sides of the aperture. On the left, there's a flat arch. You can see the sort of characteristic splay of the bricks. So each one is at an angle that both traces this invisible arch through it, but also keeps each brick from sliding down past it and failing in that way. You can see also that they've taken some of the load off of that lintel by putting an arch into the wall above it. These are called relieving arches. Invisible if you plaster the wall, but very important in taking the load of the wall above and spreading it around the window below, taking some of the load off of that flat arch. In the center, a segmental arch. It doesn't have to be a full semicircle, although those are sometimes, as we'll see, easier to build. And on the right, a combination of a marble lintel with a relieving arch above it that's taking most of the weight of the wall, spreading it around the opening below, so that relatively fragile marble lintel only has to carry the weight of the brick between it and the arch above. Now, one of the things that the Romans realized is that you could take your barrel vault, or your semicircular arch, and extrude it into a barrel vault. In other words, you could build that scaffolding to a precise radius out of timber, and you could then either build a lot of scaffolding and extend the vault, or you could build one piece of scaffolding, build an arch over that, remove the scaffold, move it, and build another arch over that, so that you could essentially extrude a vault as many times as you could move the scaffold. They realized that you could do this in a couple of different ways. So on the left, you see the diagram C is the principle of a barrel vault, where you take an arch and you bring that arch down onto very thick buttressing walls. The weight of the arch gets turned into both a vertical and a horizontal reaction. And as long as the wall is thick enough, it'll be able to both hold the weight of the arch and also to absorb its thrust. So here on the left, you see an example of a barrel vault, just an arch that is extruded along a single axis. Slightly more sophisticated idea is to take two barrel vaults and intersect them. And in this case, you get what's called a groin vault. You can see this is the interior of a converted Roman bath on the left, building that we'll talk about in a couple of lectures. You can see that there are basically two semicircular barrel vaults that intersect and that basically carve one another out. so that what you're left with is this kind of sail shape of a roof. And what builders realized was that this opened up not only, in this case, the main axis, right? You can span over 15 or 20 meters and have a grand space that you can walk through, but it also allows you to open up the cross axis. And on the right and left of the photo, you can see these giant windows, what were called thermal windows, windows for baths, therma being the Latin for bath. And the barrel vault in that direction allows you to open up not just the length of the vault, but also the sides of the vault and bring in light and probably air. This has the same problems of thrust that the barrel vault has. If you line up groin vaults, they can buttress against one another. But here, of course, going in the cross-axial direction, there are thrusts that have to again be absorbed by the thickness of the walls on the exterior. And groin vaults, like barrel vaults, can be sort of extruded along so that you can get either a bath or, in this case, a market hall. Trajan's markets in Rome had some of the earliest groin vaults that we know of, and they still exist in sort of ruined form. You can see them on the left. This is this hall in the drawing on the upper right. So stalls in the bottom that are built into the wall, a sort of milling about space in the middle that's covered by these groin vaults. And you can see that not only does that open up the long axis of the market hall, but it also opens up the sides to bring in light and to bring in air. And this is what we imagine it must have looked like. So a lot of space, but also a kind of monumental presence to the space that dignifies the commerce that's going on within it. Now, there are readings by the historian and archaeologist Lynn Lancaster that talk about why these buildings were the shape they were, or why the vaults were the shapes that they were. And it's fairly apparent that the easiest curve to build is a semicircle, right? That all you need to do is lay out on the ground with a piece of string and a pointer, a single radius, and you can use that then to build a series of timber frames and a timber formwork that allows you to build a consistently shaped semicircle. That is not the ideal structural shape. We know today that a catenary, a shape that's more like a parabola, is more efficient and more effective at carrying loads. Romans wouldn't have known that, and it's very difficult to both lay out and to build a parabolic shape out of timber, out of the materials that Romans had. And the semicircular shape is a sort of perfect balance between the ideal performance shape and something that's relatively easy to build, right, within their abilities in terms of kind of drafting, but also in terms of fabricating on the ground. On the left, you can see reconstructed what might have been the scaffolding for something like the barrel vaults that we saw before. It could be, too, that you would just build a segment of this, and when one bit of vault was done, you could discharge the scaffold and build the next. On the right, this is Lancaster's reconstruction of what the scaffolding for the groin vaults at Trajan's markets may have looked like. And again, this could have been something that, instead of being scaffolded all at once, could have been done piecemeal, right? Could have been done unit by unit. So in the last bit of the lecture, I want to look at a handful of monuments that were built basically using these two techniques, right? The barrel vault, the groin vault, and the one other thing that you can build with a semicircular arch if you rotate it instead of extruding it. Those will be the great monuments of ancient Rome, the buildings that were built by the emperors in the last part of of Roman civilization. And as we'll see, they relied entirely on brick and concrete to create their monumental forms and spaces.